So the slide is visible. Is it visible?
Yes.
Okay. So yesterday we discussed about the basics of the differential relay. Now we will continue that. Now in this case, you will see we will have this shows the CT, that is connection of the CT. We will have the primary and we will have the secondary, and this is the burden of the CT. That is the load. It is connected there wherever it is connected, and this is actually showing the secondary voltage and the magnetizing current. As you already know, it also represents the BH curve. Now here we will have the equivalent circuit of the CT. Now in this case, it is similar to the equivalent circuit of the transformer. Now in this case, we will have this is actually the resistance is this is primary resistance. This is the this leakage reactance, primary leakage reactance, which is referred to the secondary side. Since it is referred to the secondary side, then we will have the magnetizing branch here, and then we will have the secondary resistance and the secondary leakage reactance, and the burden is here, that is Z burden. Now you will see that the primary current is IP, and then it is on the secondary side it is IP divided by N, and you will see that I naught is the magnetizing branch current. So finally so this current is the magnetizing branch current, which take into which magnetizes the core, and this we have IP minus I naught is equals to I secondary. So and this voltage is the V secondary. So this is all about that. And Z burden is actually Z burden includes the resistance and inductance of relay coils and the resistance of pilot wires. That is the resistance and inductance of relay coils and resistance of the pilot wires are the leads. So this burden contains that. And as you know that this current is transformed on the secondary side, and this N is the transformation ratio in that very case, and I naught is the magnetization current. Now, and also, as you know from the equivalent circuit of the transformer, the magnetizing current is actually I naught is the non-linear function of I naught is actually the non-linear function of the voltage, and voltage in this case is V secondary. So it is the non-linear function of that. So this is the non-linear function of the voltage secondary. Now, during the normal operating conditions, you can say that the V secondary is small. We have the normal operating conditions, so this value is very less. So under the normal operating conditions, V secondary is small. So what happens when the V secondary is small? This I naught is equals to V secondary divided by this total impedance. So this I naught is very small, so we can neglect the I naught. So I naught is equals to V secondary divided by this impedance. Let it be Z magnetizing. Z magnetizing. So it is small. So it is also small. So you can say that its value is small, so it is neglected. However, at the high values of the primary current, let us suppose that when the fault occurs, and in that very case, the value of the primary current is very high. During the faulty conditions, the I primary is equals to I fault. So this is in case of the normal condition. And now, under the faulty conditions, I primary is equals to I fault, and its value is very large. And the secondary voltage in this case, this secondary voltage, it is actually the sum of this voltage and sum of this voltage. If the primary current is large, then the secondary current would be large. So V secondary in this case is equals to I secondary plus Z secondary. Let us suppose that we have the Z secondary and then we have Z burden. Let it be ZB. So this is, if this is large, that primary current is large, then definitely the secondary current would be large. And if the secondary current is large, in that very case, the V secondary is appreciable. And if the V secondary is appreciable, and I naught depends upon the V secondary. So if I primary is large, then we will have I secondary is large. So V secondary is also appreciable. And if V secondary is appreciable, then I naught is proportional to V secondary. So we cannot neglect it. So we can say that we cannot neglect it, and it is the appreciable fraction of the current transformed by the ideal CT. So we cannot ignore the I naught. So we cannot ignore that under this faulty conditions. Now, what we do is it is actually the CT equivalent circuit of a single CT. What we do, we will use this CT as in the differential protection. This is for a single this CT, equivalent circuit of a single CT. Now we will have the two CTs in the differential scheme. Now we will use these CTs in the differential scheme. That is, on the both the sides we will use this equivalent circuit. Now we will have the diagram. Now, from this, it is obvious that it is similar to the equivalent circuit what we have studied. We have the here we will have the primary resistance referred to the secondary side, then leakage inductance, then we have the secondary. All the things remains the same in that very case. And here the current is transformed. That is, the primary current is there. Then primary current is transformed by this by N, by dividing it by N. So similar is this case. So when we will have this primary current, then finally we will have primary current divided by N minus this magnetizing current of the first CT. Then here we will have this value. Now to get the value, this one IP divided by N minus this magnetizing current of the second branch, the spill current would be I naught 2 minus I naught 1. So this is the whole thing, that in the spill branch, whatever we are getting the spill current. So from this we will see that it depends upon this if the external fault current is large, in that very case the value of I naught is large, and if I naught is large, then indefinitely we will have the maloperation of the relay. So this thing is there, that in the spill path we will have the current I naught 2 minus I naught 1. So this magnetizing current is more during the external fault in case of an ideal relay. So from this figure you will see that you have seen that let us assume that both the CTs have the same nominal ratio, that is N and N in that very case. And we can see the spill current is equal to the difference between this magnetizing current And since the magnetizing current, it is because of the magnetizing current of the two CTs is vary widely. So you can say that there is the substantial spill current during the external fault, as we have discussed, and this results in the loss of stability and the maloperation of the relay. So the simple differential relay, which looks like very simple, cannot be used in practice without the certain modifications, because in the spill current we will have the magnetizing current in that very case. So this is especially true in case of the transformer protection. So we cannot use the simple differential relay without the modification. This is true in case of the transformer. That is, in case of the transformer, as you know, that in case of the transformer, we will have primary and we will have the secondary side. And the voltage of this is different. So we will have the different voltage levels. And because the currents of two CTs are different, ratio of transformation of CTs is also different. And so their designs are also different, making it impossible to get a close match between the characteristic if we are not modifying it. So this actually explains that why the spill current goes on increasing as the throw fault current increases, that is external fault current increases. Now, in case of a bus bar protection, if you take the case of the bus bar protection where we'll use the this differential scheme. In case of a bus bar protection also, in which the differential scheme is used, we will have the two CTs which are at the which are same, and the CT ratio are also same in that very case. However, the bus bar is these are actually subjected to the heavy fault currents, which tends to magnify the differences between the characteristics of the two CTs. So we cannot. So in the bus bar protection also, we cannot use the simple differential scheme. So we have to modify this to in one way or the other. So the one of the modification is the that is one modification is the percentage differential relay. So we will discuss the percentage differential relay. So in this case, we discussed that how the simple relay cannot be used, because we will have the spill current even if the external fault occurs. So we will have some kind of a mechanism so that this spill current would not be there during the external fault condition. So we will discuss that. Now we will discuss the percentage differential relay. So we will have the percentage differential relay. Now what happens that in the simple relay, what we do, if we have the restraining torque proportional to the external fault current, if we will have the restraining torque proportional to the through fault current, we will have the restraining torque proportional to the through fault current, and then we can say that the operating torque is proportional to the spill current. So operating torque is proportional to the spill current. So that logic we have to use in that. Now this idea can be implemented by the percentage differential relay. And now in this case, we have the equipment under protection, we have the CT, this CT, and then we have the second CT. And these are actually the restraining coils which are used in that. So this is the conceptual diagram, and this is how it can be implemented by the this how it can be implemented by the beam structure. So in this case, the relay has actually this relay, that is a restraining coil, which is tabbed at the center. Here you will see that this is tabbed at the center. This is A and B, that is connecting here A and B. So it is tabbed at the center and forming the equal, that is, we can say that it forms the equal section with the two, that is the number of turns equals to nr divided by 2 and nr divided by 2. Here you can say that is nr divided by 2 and nr divided by 2. And the restraining coil is actually connected in the circulating current path and receiving the external fault current. So it is connected in the circulating, that is it is connected in the circulating current, which is receiving the this external fault current. So these restraining coil are connected in circulating path receiving the through fault current. So it is connected in the circulating path, receiving the through fault current, and it has the number of turns nr, and since we have center tapped, so it is nr by 2 and nr by 2. Now the operating torque has n naught number of turns. This is the operating torque, that is n naught number of turns, and it is connected in the spill path. That is, it means that it is connected in the terminal C, that here we have the terminal C, and then center tapped here. It is center tapped here. So this operating coil, it has n naught number of turns, and you can see that it is connected in the spill path. So it is connected in the spill path. Now from that, what we do, we will develop a torque equation. We will develop a torque equation. Now the ampere turns on the left hand side of the restraining coil. That is, we have the restraining coil here, and on the left hand side of the restraining torque, we will have the ampere turns, that is the current that is going through it is I1. So ampere turns on acting on left hand section of a restraining coil. So what are the ampere turns in that very case? That is, we will have nr by 2 into I1. Then on the right hand side, it is same. In the right hand side of the restraining coil, we will have nr divided by 2 I2. So total ampere turns equals to nr divided by 2 I1 plus I2. Now, these are actually the ampere terms. Now, torque is proportional to the square of the flux, and the flux is proportional to the ampere turn. So, torque produced by the restraining coil. So, this is ampere turn. So, flux is proportional to ampere turn. So, we can use one proportionality factor M, and then we will have nr I1 plus I2 divided by 2, and M is the constant of proportionality. Now, Now you will see this is the restraining torque. However, if we are also using the spring, in this case we have used the spring, so it also acts opposite to that of the operating torque. So that we have also included that. So the total torque in that very case, total restraining torque in that very case would be N2 I1 plus I2 divided by 2 plus T spring. Now, operating torque. What is operating torque? The number of turns in that very case is N naught. So proportionality factor, so let us suppose that we use M. So N naught, and what is the current in that? The current would be, so ampere turn. So it is proportional to a square of this flux. So it is square of the flux. So we have to use the square here. So then we will have the operating torque. In this case, the operating torque is equals to, as you see, it is I1 minus I2. So here N naught into I1 minus I2 whole square. So this is the restraining torque, this is the operating torque, and the relay trips if this operating torque is greater than the restraining torque, and relay is on the verge of operation when both are equal. So when they are on the verge of operation, when T restraining and T operating are equal. So we can have T restraining is equals to T operating, and when we solve it, finally we are getting I1 minus I2 equals to K I1 plus I2 divided by 2, and K in this case is NR divided by N naught. So NR divided by N naught. So finally we are getting this. However, we have, in this case, we have neglected the T spring. So the final equation, if we are not neglecting the T spring, then it is given by, if we are not neglecting the T spring, then the final equation we are getting I1 minus I2 equals to K. K in this case is NR by N naught, NR by N naught, number of turns of the restraining coil and operating. And then we will have K I1 plus I2 divided by 2 plus K naught. So this is we are getting. So this is actually the this equation is actually the equation of a straight line. So this is an equation of straight line, that is y equals to mx plus c. This is, we have considered this value. We have considered the spring value of that. Sorry for the interruption. There was some call. So this is y equals to mx plus c. Now here we will have the y in this case. You will see that y in this case is the spill current, and this x in this case is the through fault current I1 plus I2 divided by 2. And this slope, actually, it is decided by the number of turns of restraining coil divided by the operating coil. Um, so you will see that this is the characteristic. This is the characteristics of a simple differential relay, and this is the external fault characteristic that we have also discussed in the previous lecture. So this is the simple differential relay characteristics. That is, it is a straight line in that very case. Uh, uh, Now if you see that these are the characteristics, these are the new characteristics of the relay that that is come into picture because of this differential scheme, because of this y equals to mx plus c. So this is the straight line. This is actually the straight line with a slope of nr divided by n naught and the intercept of k naught. Here we will have the intercept k naught. Now you will see in the simple differential relay, this is actually the line of the simple differential relay, and before that this was the trip region and this was the restraint region. Now here what we have done with the coming of picture in of this this restraining coil, what we have done, we have increased the slope. We can adjust the slope, and this is the trip region and this is the restraint region. In that very case, you can say that all the points which represents above this line, these are under the trip region. In this case, operating torque is greater than the restraining torque. Operating torque is greater than the restraining torque, and here and it falls in the trip region, and here we will have the this points which are below that line belongs to the restraining region. So you can see from this it is observed that the spill current must be greater than the definite percentage of that is through or the external fault current. That is, spill current must be greater than the definite percentage of through fault current for relay to operate. That is, in that very case, the spill current, if you see, this is the spill current, it must be greater than the definite percentage of through fault current for the relay to operate, and that's why it has the name as the percentage differential relay. Percentage differential relay. That is, this is the through fault current, and this spill current, it must be greater than the definite percentage, and that this percentage is actually decided by this k. This percentage is decided by the k. So this must be greater than this percentage of through fault current for the relay to operate. So that's why the name is the percentage relay. And the you can say that the slope of the relay in that very case, this slope of the relay is actually expressed as the percentage, and slope of, if you have the slope of 0.4, then it is expressed, that is 0.4 means that 40% of the slope. So it is the 40% of the slope. So, what is the main idea behind this relay? The main idea behind this relay is that it doesn't have a pickup value. It doesn't have a minimum pickup value. That is a constant pickup value, you can say. It doesn't have the constant pickup value. That is, in the simple differential relay, the pickup value was constant. This was the pickup value, minimum pickup value. This was here. Now, in this type of relay, it doesn't have the fixed pickup value, and the relay automatically adapts to the pickup value to the which depends upon the through fault current. Now, as you see, as the through fault current goes on increasing, the pickup value also goes on increasing. So it means that as the through fault current is increasing, we cannot ask the relay to we can ask the relay to take it easy, and by introducing the restraining torque, which is proportional to the that is circulating current torque. So you can say that as the fault current is increasing, in that very case, this pickup value is also increasing. So it also improves the stability, and the stability of the differential relay. You can say that it is much better than the simple differential relay that we have discussed in the previous lecture. And this restraining winding is also known as the biasing winding, as we have used restraining winding. It is also known as the biasing winding. It is also known as the biasing winding because we bias the relay towards the restraint. So we bias the relay towards the restraint, and this is also known as the this type of characteristic is also known as the percentage bias. It is also known as the percentage bias. So it is also known as the percentage bias. So from this we will observe that this is the simple differential relay characteristics, and by using the differential protection, using the percentage differential relay and adjusting the slope of it, what we have adjust the slope of the pickup value of the relay. So the slope of the pickup value is automatically adjusted. This not the slope, but the minimum pickup value is automatically adjusted. We have adjusted the slope, that is this n r divided by n naught is in our hands. However, the minimum pickup value is adjusted. Is automatically adjusted. So minimum pickup value is automatically adjusted. Now here you have seen this characteristics, external fault characteristics. Now this is the internal fault characteristics with a slope of 200. So how this internal fault slope can be calculated? Now let us suppose that internal fault is there in the single end fed system. So in that very case, if this we have the single end fed system, then in that very case the current I2 will be equals to 0, that it will not contribute any current, and the spill current in that very case would be I1, because I2 is equals to 0. So we will have the spill current I1 minus I2. So spill current is I1 in that very case, and the circulating current, this is the spill current. Now the circulating current is actually I1 plus I2 divided by 2. So you will see that's I2, since I2 is equals to 0 in case of the internal fault. So this is, we neglect this thing. So the we will have the circulating current I1 divided by 2. So spill current in this case is equals to I1, and the circulating current is equals to, and the, let us suppose circulating current is equals to, you can say that it is I1 by 2, that is I2 is equals to 0 in that very case. So this is the spill current and this is the circulating current. Now if we compare the two, then in that very case you will see that the spill current will be 2 times the circulating current. So spill current equals to 2 times the circulating current. So this is the spill current and this is 2 times the circulating current. So you can have the slope of 2 here. 2 of slope means we have the 200% slope. So how we can calculate? Now in case of a single end-fed system, what happens that I2 is equals to 0. So spill current equals to I1. Circulating current is I1 by 2. And then spill current is equals to 2 times this circulating current. So here we have the y equals to mx plus c. So m slope we are getting in this case 2. So during internal fault, you can say that the spill current will be 2 times the circulating current, and it has a slope of 2 and expressed as 200%. So, so there is one more quantification of whatever. So the minimum, there is one more stability ratio we have to discuss. So minimum internal fault current, you will see that minimum internal fault current below which the scheme will not respond. This is the minimum internal fault current below which the scheme will not respond. That is, you can say that this is known as the IF minimum internal, and the maximum through fault current, that is this one, that maximum through fault current above which the scheme will malaprate is given by IF maximum external. As we have discussed in the previous lecture, the stability ratio is given by the stability ratio, that is the stability ratio is equals to IF maximum external divided by IF minimum internal. So greater be the value of stability ratio, greater is the stability of the system. So so in this case, so you have seen that the percentile differential relay can be made immune to malapration through the external fault thing by increasing the slope of the characteristics. So block diagram of the percentage differential relay. So here we will have the this block diagram for percentage differential relay. In this case, it will have the two settings. That is the slope setting. As you know, that slope can be adjusted by NR by N naught. So slope setting is there, and minimum pickup setting is there. The slope is adjusted by this adjusting the changing the tapping of the restraining coil. You can adjust that here we have the tapping of the restraining coil 1 2 and 3, here 3 2 1 1. So we can change that. And however, if the both the halves of the restraining coil, the symmetry must be maintained in both the cases. And the minimum pickup value, it can be adjusted by changing the tension of the restraining spring. So minimum pickup value can be adjusted by changing the tension of a restraining spring. So this is about the differential relay. Now, before concluding that, we will discuss a relay which is also known as the earth leakage protection relay. Earth leakage protection. Now, what is the basis behind that? That because of the many of times, if you see that because of the insulation failure of the chassis of the equipment, let us suppose that we have the equipment and there are wires within the equipment. Let us take a hypothetical case. This is equipment and this is the chassis of the equipment. So, because of the insulation failure of the chassis, let us suppose that these are the wires in that very case, and because of the insulation failure of the failure, the chassis of the equipment becomes live. What it means, this causes the leakage current to the earth. Since chassis of the equipment is always connected to the earth, and because of this insulation failure, even the wire, since it is connected to the earth, so there is the leakage of the current to the earth from the chassis of the equipment, like you will see. So, however, this leakage current may be too small. This leakage current is too small. It is too small for the overcurrent relay to operate. So, overcurrent relay cannot operate. So the value of this leakage current will be too small for the overcurrent relay to operate, and this actually poses a danger to the personnel who actually come in contact with the chassis of this equipment. So it means that this we cannot have small. The current is very much small, so that the overcurrent relay cannot operate. If suppose there is the insulation failure within the equipment, and the equipment is always connected to the ground. So, however, to prevent, however, one scenario must be there. One scenario we can say that if this chassis is not grounded, let us take the second scenario, that this is not grounded. In that very case, and then we have the insulation, it is grounded. Initially, in the first case, we assume that it is grounded. However, the overcurrent relay will not operate because the value of the leakage current in that very case is very small. Now, if in case the chassis of the equipment is not grounded, in that very case, the relay will not trip because we don't have the leakage. Leakage current is small, and we don't have the current which is flowing through it. And now let us suppose any person which is coming in contact with it, let us suppose that anyone touches that, any person touches that, in that very case, and whose body is in connection with the earth. Let us suppose that that person's body is in connection with the earth. Then in that very case, as the person's body will come in contact with the earth, it touches the cheeses, it will get the path to for the earth. That is, path of the earth is available, and let us suppose that leakage current is of a sufficient magnitude. So if the somewhere the overcurrent relay is connected, then in that very case it will trip. Overcurrent relay will trip in that very case. Whenever the person this touches that, and and let us suppose that that person is grounded in that very case, and then we have the overcurrent relays, and definitely the overcurrent relays will trip, and this person will, of course, you can say, it will receive the electric shock before it is tripped. So this is the scenario. Now, to prevent that, what we have to do, we have to use the earth leakage relay or the current balance relay. So we have to use the earth leakage relay or the current balance relay. Now, in this case, here shows the schematic of this earth leakage protection for a single phase load. In this case, let us suppose that that is the actually this relay. It consists of the toroidal core, if you see, and it has the two identical windings, that is A and the B windings, having number of turns, equal number of turns, and number of turns, let us suppose. And then we have another coil, that is C, which is known as the pickup coil, and wound, and it is connected to the overcurrent relay in that very case. Now, the phase and neutral, here we will have the phase and the neutral leads are connected to these windings, so that these will carry the equal currents under the normal conditions. Under the normal condition, the phase and neutral wires will carry the equal current, and there is no magneto-motive force, no imbalance of the magnetic motive force acting on this toroidal core, if you see. Now, the flux linked with the pickup coil is therefore zero, and no voltage is induced in it. And as a result, no overcurrent relay is tripped in that very case. Now, let us consider the situation in which we will have, let us suppose that we have the leakage current I, leakage in that very case. Now, the current in the phase wire, in this case, this is the leakage current. Now, the current in this phase wire is now equals to, it is equals to, this is N neutral, this is net neutral wire, plus the leakage current. So the phase wire current is the sum of this neutral current and the leakage current. Now, the MMF acting on this toroidal core in that very case would be equals to, it is equals to I phase minus I neutral into N. So this MMF is acting on this coil, that is, or you can say that N into I leakage. So this MMF is acting on this coil, and MMF actually sets a flux in the core, causing a voltage to be induced in the pickup coil, and you can see that the overcurrent relay therefore get energized and it get trips up. So whenever the fault occurs and whenever the leakage current is there, in this case, you will see whenever the leakage current is there, this overcurrent relay will trip, and this type of protection is known as the earth leakage relay or the current balance relay. Now, this is in case of the single phase loads. Now, in case of the three phase loads, what this is the schematic for the three phase load. And in case of the three phase loads, now three phase leads are actually threaded through the CT core. This is the core of the CT. So these three phase, these are actually threaded through the CT core, and the pickup winding is provided Here we will have the sorry, the pickup coil is provided, which is connected to the overcurrent relay in case of fault is there in the system. And now during the balance, during the normal operating condition, you will see that the phasor sum of three phase currents is equals to 0. Ia plus Ib plus Ic is equals to 0 during the balanced conditions, and as a result, no net MMF is induced in this pickup coil, and the overcurrent relay remains unenergized. However, during the earth leakage, whenever there is the leakage in the system, then in that very case, this Ia plus Ib plus Ic is not equals to 0. So a voltage, so you can say that a voltage is induced in the pickup coil, which causing the overcurrent relay to operate. Now, this is the three wires we have used, and we have this iron core structure, which is these three wires pass through the iron core structure. However, it can cause maloperation in case of let us suppose that we have the unbalances in the supply or the load, and this can, however, be avoided if the neutral is also threaded through this core. So that is one thing that you can use. So this is about the earth leakage relay and the current balance relay.